Download this code from codegive.com, link in the description below. OK, let's dive deep into the concept of stationarity in time series analysis, including the augmented dickey-fuller, ADF, test, the phillips-perron, PP, test, and the idea of integration. I'll provide comprehensive explanations and practical Python code examples using the statsmodels library. What is stationarity? Stationarity is a crucial concept in time series analysis. A time series is considered stationary if its statistical properties, like mean, variance, and autocorrelation, remain constant over time. In simpler terms, mean the average value of the series doesn't change systematically over time. There is no trend. Variance the spread of the data around the mean remains consistent. The series does not have increasing or decreasing volatility. Autocorrelation the way values at different points in time relate to each other doesn't depend on time. The correlation between values at a certain lag is stable. Why is stationarity important? Many time series models, like ARIMA, exponential smoothing, and others, are built on the assumption of stationarity. If your time series is non-stationary, the results of these models can be misleading or unreliable. Here's why. Spurious regression regressing to non-stationary time series can often lead to a high R-squared value and statistically significant coefficients, even when there's no real relationship between the variables. This is called spurious regression. The models pick up on shared trends, not true causal relationships. Unreliable forecasts. Non-stationary series can have unpredictable behavior in the future, making forecasting difficult. Trends or changing variance can cause your forecasts to drift or have wide confidence intervals. Model assumptions. Stationarity is often required for statistical tests used in time series modeling, example tests to determine the order of ARIMA models. 2. Types of non-stationarity. There are two main types of non-stationarity. 1. Trend non-stationarity. The time series has a systematic upward or downward movement over time. This violates the constant mean assumption. 2. Variance, heteroscedasticity, non-stationarity. The variability of the time series changes over time. This violates the constant variance assumption. For example, the series might have periods of high volatility followed by periods of low volatility. 3. How to detect non-stationarity. There are several ways to determine if a time series is non-stationary. 1. Visual inspection. Plot the time series data. Look for trends, seasonal patterns, or changes in variance. 2. Summary statistics. Calculate the mean and variance for different segments of the time series. If these values are significantly different across segments, it suggests non-stationarity. 3. Autocorrelation function, ACF, and partial autocorrelation function, PACF, plots. These plots show the correlation between a time series and its lagged values. For stationary series, the ACF typically decays quickly to 0. For non-stationary series with a trend, the ACF will decay slowly. 4. Unit root tests, formal statistical tests. These are the most reliable methods for assessing stationarity. The most common tests are the augmented dickey-fuller, ADF, test and the phillips-perron, PP, test. 4. Augmented dickey-fuller, ADF, test. The ADF test is a statistical test used to determine if a unit root is present in a time series. A unit root implies non-stationarity. The test works by fitting an autoregressive, AR, model to the data and examining the coefficient of the lagged level of the series. Null hypothesis, H0 the time series has a unit root, i.e., it is non-stationary. Asterisk alternative hypothesis, H1 the time series does not have a unit root, i.e., it is stationary. Interpreting the ADF test results asterisk. Asterisk p-value asterisk the p-value is the probability of observing the test statistic, or a more extreme value, if the null hypothesis is true. A small p-value, typically less than a chosen significance level, example 0.05, indicates strong evidence against the null hypothesis. Asterisk test statistic asterisk the ADF test statistic. It's compared to critical values. Asterisk critical values asterisk these are values that define the rejection region. If the test statistic is more negative than the critical value, you reject the null hypothesis. Asterisk decision rule asterisk. Asterisk if p-value equals significance level, example 0.05, reject the null hypothesis. The series is likely stationary. Asterisk if p-value significance level, fail to reject the null hypothesis. The series is likely non-stationary. Asterisk trend and constant asterisk in the ADF test, you can specify whether to include a constant term, drift, or a trend term in the regression. This is important because the appropriate model can affect the test results. V. Phillips-perron, pp. test. The Phillips-perron, pp. test is another unit root test similar to the ADF test. However, pp tests handle the issue of serial correlation and heteroscedasticity in the error term differently than ADF tests. Instead of adding lag difference terms to the regression, as in ADF, pp tests use non-parametric statistical methods to correct for serial correlation and heteroscedasticity in the error term. Asterisk null hypothesis, H0 the time series has a unit root, i.e., it is non-stationary. Asterisk alternative hypothesis, H1 the time series does not have a unit root, i.e., it is stationary. Interpreting the pp test results asterisk. The interpretation is the same as for the ADF test, compare the p-value to a significance level. A small p-value suggests stationarity. The decision rule is asterisk if p-value equals significance level, example 0.05, reject the null hypothesis. The series is likely stationary. Asterisk if p-value significance level, fail to reject the null hypothesis. The series is likely non-stationary. Key differences between ADF and pp tests asterisk. Asterisk handling serial correlation asterisk ADF tests handle serial correlation by adding lag difference terms to the regression equation. pp tests use non-parametric corrections to the test statistic. Asterisk robustness asterisk pp tests are generally considered more robust to serial correlation and heteroscedasticity than ADF tests. Asterisk computational cost asterisk pp tests are generally computationally simpler than ADF tests. 6. Making a time series stationary, differencing. If a time series is non-stationary, you can often make it stationary by differencing. Differencing involves calculating the difference between consecutive values in the series. Asterisk first order differencing asterisk diff x equals xt, xt1, subtract the previous value from the current value. This removes a linear trend. Asterisk second order differencing asterisk diff x, apply first order differencing twice. This can remove a quadratic trend. Asterisk seasonal differencing asterisk xt, xts, subtract the value from s periods ago from the current value. This is useful for removing seasonal patterns, where s is the length of the seasonal cycle. The number of times you need to difference a series to make it stationary is called the order of integration, denoted by D in ARIMA models. If a series needs to be differenced once to become stationary, it is said to be integrated of order 1, denoted I, 1. A stationary series is considered to be integrated of order 0, denoted I, 0. 7. Code examples, Python with stats models. Explanation of the code asterisk. 1. Data generation asterisk. We create a non-stationary time series with a linear trend. We also generate seasonal data and data with increasing variance. 2. ADF test function asterisk. The perform underscore ADF underscore test function takes a time series and a title as input, performs the ADF test using dickey-fuller, and prints the results, including the test statistic, p-value, and critical values. 3. PP test function asterisk. The perform underscore PP underscore test function does the same as ADF, but implements the KPSS test with KPSS. 4. Differencing function asterisk. The difference function calculates the difference between consecutive values in the series. 5. Running the tests asterisk. The code first performs the ADF and PP tests on the original non-stationary data. Then, it applies first-order differencing, and performs the tests again on the differenced data. Finally tests on the seasonal data with seasonal difference and the data with increasing variance with Box-Cox transform. 6. Plotting asterisk. The code plots the original and differenced time series to visualize the effect of differencing. 7. Box-Cox transformation. Applied a Box-Cox transformation to stabilize variance. 8. Additional tips and considerations asterisk asterisk. Asterisk significance level asterisk. Choose an appropriate significance level, alpha, for your hypothesis tests. Common values are 0.05 or 0.01. Asterisk trend and constant in ADF asterisk. Pay attention to whether your time series has a trend or a non-zero mean, constant. Use the regression parameter in the dickey-fuller function to include a constant, c, and slash or a trend, ct, in the test. If you include these when they are not needed, it could lower the power of the test. Asterisk order of differencing asterisk. If first order differencing doesn't make the series stationary, try second order differencing or higher. Overdifferencing can introduce artificial correlations. Asterisk seasonal adjustment asterisk. If you have seasonal data, consider seasonal decomposition, using statsmodels.tsa.seasonal_decompose, to separate the trend, seasonal, and residual components before differencing. You can then difference the trend component or use seasonal differencing. Asterisk transformations asterisk. If the variance of your series is not constant, heteroscedasticity, consider transformations like the Box-Cox transformation or taking the logarithm of the data to stabilize the variance. 9. Integration. As mentioned earlier, the order of integration refers to the number of times a time series needs to be differenced to achieve stationarity. Asterisk I, 0. A series is integrated of order 0, I, 0, if it is stationary in its original form. Asterisk I, 1. A series is integrated of order 1, I, 1, if it becomes stationary after first order differencing. Asterisk I, 2. A series is integrated of order 2, I, 2, if it becomes stationary after second order differencing, and so on. The order of integration is important in time series modeling, especially when using ARIMA models. The D parameter in ARIMA, P, D, Q, represents the order of integration. In summary, understanding stationarity is fundamental to time series analysis. By detecting non-stationarity using visual inspection, ACF/PACF plots, and formal unit root tests, ADF and PP, you can apply appropriate transformations, differencing, Box-Cox, to make your time series stationary and prepare it for modeling and forecasting. The order of integration tells you how many times you need to difference your series to achieve stationarity, which is crucial information for building accurate time series models. Remember to always visually inspect your data and carefully interpret the results of the statistical tests.